Dear students, now I am going to explain to you the very next topic of electrical conductivity in metals, and that is the semiconductor physics. That is, we are going to learn in this topic how conductivity that is taking place in the case of a semiconductor. We are all aware a semiconductor is a material whose conductivity lies between conductor as well as insulator. This is what we know, because a conductor is one which allows the charges to pass through. An insulator is one which do not allow the charges to pass through. But the semiconductor, the word itself tells us that its conductivity lies between conductor as well as the insulator. That means the conductivity lies almost between 10 to the power minus 6 to 10 to the power plus 8 ohm per ohm meter. This is what the conductivity of a material. Now, why this conductivity changes from such a smaller value to such a larger value? It purely depends on what is called as a temperature. At very low temperature, the same semiconductor act like an insulator. Naturally, its conductivity is very small. But at a very high temperature, the conductivity of the same material is going to become the conductor. Naturally, the conductivity increases. There is a reason that the conductivity in the case of a semiconductor just based on the temperature. Now, how do we able to explain the conductivity in the case of a semiconductor? And this can be explained just based on what is called as a band theory, which you already learned. Now, in my previous class, I had very clearly said that in the band theory, there are formation of the bands. And we have learnt about the band at the topmost level where the electrons are completely filled, or what is called as a valence band. It is the highermost band where the electrons are completely filled. And above than that, there is one more band, and the band is absolutely empty at zero temperature, and that is what is been named as a conduction band. And between these two bands, there is a gap, and this is called as a forbidden energy gap. Now, based on this forbidden energy gap, the materials are generally being divided. So, how do you able to divide the materials into these categories? We are aware, if you consider it as a conductor, we have a valence band here. In the case of a conductor, we have a valence band here, and the conduction band is going to overlap. It is going to overlap. This is the conduction band where there is no energy gap here. So, energy gap between the two is going to be zero, and this is going to become a conductor. But if you consider it is a insulator where the valence band and the conduction band has got a large gap. It has got a large gap where the gap is going to be greater than around 3 electron volts. It is greater than 3 electron volts. Then this material is what we call as an insulator. Insulators. But if the energy gap between a valence band and the conduction band is lesser than around 3 electron volts, then such kind of materials are what we call as a semiconductors. This is what we call as a semiconductor. Therefore, in the case of a semiconductor, the energy gap is very small. So at absolute 0 Kelvin, we know that all these bands are completely occupied. All these bands means electrons are completely occupying this, where it is empty at absolute 0 Kelvin. But being there is a small gap between the two, at a temperature above 0 Kelvin, it is possible that the electrons are able to jump here and they are able to conduct. Hence, the conductivity of a semiconductor just purely depends on the temperature. Now the question is this: in this kind of semiconductor, how much is the energy gap? Let us try to take the example of silicon. Silicon is a very good example semiconductor which has got an energy gap of around 1.1 electron volt. Germanium also is one of the very good example, has got 0.7 electron volts. And other than that, we have maybe gallium arsenide or gallium phosphide or maybe gallium nitride or selenium. So these are the various examples where the energy gap may lies between around 1.3 around 1.9 electron volts. So having energy gap smaller, maybe of this range, such kind of materials are what we call as the semiconductors. Now in the case of semiconductor, there are two different types of semiconductors we have already studied. The one is called as the intrinsic semiconductor, and the second one is called as an extrinsic semiconductor. Now what is an intrinsic semiconductor? A semiconductor where in its purest state, in its pure state is what is called intrinsic. That means there are no additional elements or atoms present in such kind of materials. Then it is called as an intrinsic semiconductor. But if you are able to add some kind of impurities to it, then such kind of materials are what we call as an extrinsic semiconductor. Now, what is the major difference that you find between the intrinsic as well as extrinsic? Now, to understand that, let me try to take an example of silicon. We know every semiconductors are tetravalent. Tetravalent means it has got 4 electrons at the outermost shell. They are called tetravalent. And every semiconductors are tetravalent. Whether it is germanium, whether it is gallium arsenide, whether it is boron, they're all 4 electrons at the last orbit. Now, when one atom is been surrounded by some other atoms, so I have one more silicon here, which also has got tetravalent here. There is one more silicon atom here, which has got 4 electrons here. Like that, I can take as many number of electrons here, Every one electron of one atom is going to bond with the other neighboring electron. So this is called as a covalent bond. This is the covalent bond between the two electrons. So every one electron of one atom is going to bond with the neighboring electron. There is a reason that there are not even a single free electron that is going to be present at absolute 0 Kelvin. Hence this material is going to become an insulator. Now what exactly going to happen if I am going to increase the temperature of this material? If I try to increase the temperature of this material, the electrons will gather the energy, and at certain temperature the covalent bonds starts going to break. And as soon as a covalent bond is going to break, this electron is going to be freed out and electron comes out. And naturally there is a vacancy being created here, and that vacancy is what is being named as the hole. Therefore, in the case of intrinsic semiconductor, that you can see, as you increase the temperature, there is one by one bond is going to break and one electron is going to freed out, and for every one electron freed out there is a hole being created, such that the number of electrons and the number of holes are always equal. They are always equal. Number of electrons and the number of holes are equal. Therefore, here you are not able to change the number of electrons and the number of holes, since electrons as well as the holes are the charge carriers, but the number of electrons and the number of holes are equal, and there is no called majority and minority charge carriers. So both are equal carriers of charges. So this is one of the advantage, having the number of electrons and holes equal, but it is also have a disadvantage that you can't have different number of electrons as well as the holes. But in the case of extrinsic semiconductor, where we are able to add some kind of impurity to it. Suppose I can add a trivalent impurity or a pentavalent. Trivalent maybe it is aluminum because it has got 3 electrons at the last orbit, or phosphorus, it has got 5 electrons at the last orbit. Now when you add trivalent material for this silicon, suppose I will have an aluminum here which has got 3 electrons here, and it has been surrounded by all these silicon atoms, but these silicon atoms are all tetravalent, and every one electron of a silicon is going to bond with the neighboring. But the problem is that aluminum doesn't have any electron to bond with the silicon, hence it is going to create a hole, it is going to create a vacancy. So it is able to bond with this. Naturally, there is one hole is already been created in the absence of the temperature. Now if I increase the temperature, maybe this bond is going to break and an electron is going to free out, and there is one more hole is been created, and you can see the number of holes are going to be greater than the number of electrons freed out. Therefore, when I increase the temperature, one by one bond is going to break, and electrons are being freed out, there are holes are being created, but at any instant the number of holes are going to be greater than the number of electrons. And naturally, being more number of positive charges, this is called to be a p-type semiconductor. It is a p-type semiconductor, and similar thing been observed even in the case of n-type semiconductor, where a pentavalent element which is to be added, where there is one excess electron. Naturally, in such kind of materials where we have number of electrons are going to be greater than the number of holes, and this is going to become a n-type semiconductor. So this is how the intrinsic and extrinsic semiconductor. And the advantage of this material is that you can have more number of holes or you can have more number of electrons. If there are more number of holes are there, this is the majority carries, and if there are more and this is the minority, and if there are more number of electrons are there, electrons are the majority and holes are exactly the minority charge carriers. Now this is how exactly the charge carrier that is going to take place. Now in a bulk material, whether it is a majority charges or minority charges, they are able to move from one corner to the other corner. When an electron is going to move in one direction, we assume that there is a hole being created in the opposite direction. And naturally, the direction of the current and the electron and the direction of the holes are totally in the opposite direction. Therefore, there are two kinds of current. One is exactly the electronic current, and one more is called as a hole current. So there are two kinds of current that are being present. So the net current is always equal to the electron current and the hole current that you would see in the case of a semiconductor, whether it is a pure semiconductor as well as a impure semiconductor. Now let us try to understand what is the significance of the Fermi level in the case of semiconductor, and how exactly the semiconductors are able to conduct, which I will try to explain to you in the coming video.